Hello friends, today we'll start with next case of welded eccentric connections. Load perpendicular to the weld group. Directly we'll start with the problem. Once we take the problem and the diagrams, you'll understand how to solve and how to consider the loads. Determine the size of the weld required for the bracket connection shown. Let this vertical element be one column. This is the flange. This is the web. Another beam is connected to this column, flange of this column. So these two are the flanges. This middle portion is the web. The load acting is 150 kilonewtons. Let that eccentricity be 100 mm. I am going to provide welding at flange and at web. So this is the welding at the flanges and this is the welding at the web. Let this dimension be given as 400 mm. This weld dimension, weld depth of flange is 300 mm. Now I am going to draw a front view of this. This is the flange. I am going to show it here. This is the web. This weld is provided here on the flange of the beam. This weld, it is provided here at the bottom flange. This web welding this dimension is 300. Let this dimension be 250. So I have to determine the size of the weld required for this eccentric welded connection. So let us start with the solution. First, factored load. (1.5 into 150), 225 kilonewtons. Now let me calculate weld length. Total weld length will be 250 plus 250, 500 plus 300 plus 300. 2 into 250 plus 2 into 300, 1100 mm. Now my next step will be to draw a detailed diagram of only the weld. So this portion, these two and this, I am going to draw a detailed diagram for this, an enlarged view. Weld at the top of the flange, weld at the bottom of the flange, weld at both the sides of the web of the beam. So this is the diagram of the weld. Let this dimension be 250. Now let me show IXX and IZZ axis. Its CG are at the center. Similarly, its CG is at the center. Now if you look at this weld portion, this is symmetrical about y-axis as well as symmetrical about x-axis. So very easily I can draw this CG axis. Since this is a symmetrical type of weld, there is no need to find IXX or IYY. This total dimension is 400, 200, 200. This weld dimension from here till here, this is 300, this is 200. Let this dimension be maximum distance of weld from XX axis, that is shown as Y max. Now I have to calculate moment of inertia. IXX. Now look at this diagram. First let me write the equation for these two flange welds. I am going to find IXX. So parallel to XX is B, perpendicular is D. BD cube by 12 plus area into CG distance square. B is 250 into D cube. This is nothing but throat thickness T. BD cube by 12 plus area 250 into T into distance square, distance of CG of this element from XX. So this dimension is 200. If you look at this diagram, element 1 and 2, so I am going to multiply these values by 2 plus, let me write for these. When I am writing IXX, this dimension parallel to XX becomes B and this becomes D. So this is nothing but throat thickness T. So this becomes B, that is T into 300 cube by 12 plus area 300 into T into distance. Now look at this distance. This axis and this, they are almost overlapping each other. There is very little difference between these two. Hence this can be equated as 0. Practically this is 0. Just for showing sake I have shown it like this. But if you look at the actual weld, this dimension is almost 0 into 0. Now neglecting T cube terms, as well as this becomes 0, and again these are two elements, so I am going to multiply this equation by 2. So I get value IXX is equal to 24.5 into 10 raised to 6 T. Now here in this case of problem, there is no need to calculate IYY, because IYY is not going to contribute towards the strength. Strength depends only on IXX criteria. So we do not calculate IYY. So IP is equal to IXX. Now let us calculate moment. Moment M is equal to P into E. Load into perpendicular distance, eccentricity E. Now look at this diagram. Load is 150 into 1.5, that is 225 into 100. So I am going to write this M is equal to P is 225 into 10 raised to 3 newtons into 100. So this is the moment acting on the joint. Now let us calculate F1. Direct stress F1 is equal to P divided by L into T. Load divided by length of weld into throat thickness. So load is 225 into 10 raised to 3 divided by length of the weld 1100 into throat thickness. I get the value 204.5 by T. Next, load due to bending stress. Bending stress F2 is equal to M into Y max divided by IXX. This is the equation to find load due to bending stress. Moment M into Y max. Y max is perpendicular distance from XX axis, farthest point of the weld, into IXX. So writing the equation, 225 into 10 raised to 3 into 100 this becomes m divided by Ixx. So Ixx is 24.5 into 10 raised to 6 T into Ymax. Ymax is 200. So I get the value F2 is equal to 183.67 divided by T. Now I have to equate this resultant. I have to find the resultant and equate to characteristic strength. Resultant R is equal to F1 square plus F2 square, and for joint to remain stable, this resultant R should be less than or equal to characteristic strength of weld. So I will write the equation under root 204.5 by T bracket square plus 183.67 by T bracket square. This I am going to equate that to characteristic strength, that is 410 by, or I will write the equation Fu by root 3 into gamma mw, that is equal to 410 divided by root 3 into 1.25 for shop weld conditions. So I will square these and these. 204.5 by T bracket square is equal to plus 183.67 by T bracket square is equal to 410 by root 3 into 1.25 bracket square, that is equal to 189.37 bracket square. 204.5 by T bracket square plus 183.67 by T bracket square is equal to 35,861.33, or let me expand this, 41,820 by T square plus 33,708.9 by T square is equal to 35,861.33. 75,828.9 by T square. I am going to add these two terms, is equal to 35,861.33. T square is equal to 2.1, or T is equal to 1.45. We have the equation T is equal to 0.7 S, or S is equal to 2.07 mm. Provide minimum weld size S is equal to 3 mm. This completes the solution. Thank you.